Hello, and welcome to our project, an interactive conversational agent to aid human learning. Our project focuses on improving current methods related to knowledge state modeling. Knowledge state modeling attempts to quantify what a student knows and does not know. Knowledge modeling has been studied extensively by Duolingo for its ability to improve second language acquisition systems. Current state-of-the-art techniques do not leverage knowledge modeling effectively. By intelligently selecting exercises based on the current knowledge state of the student, online learning modules can greatly amplify their teaching capabilities. Next slide, please. We attempted a novel implementation task in which we create a model that selects exercises based on the user's current knowledge state to maximize learning. We use the dataset available from Duolingo's 2018 Second Language Acquisition Modeling Competition for this task. This dataset has about 4 million examples. The baseline models for knowledge tracing are also based on top performers from this competition. The main assumption we use for this task is that learning an item is dependent on how many times it is seen by the user.
Okay, now going on to the approach that we are following for this particular project. So in our implementation, we will be making use of three main components. Firstly, we will make use of a knowledge tracing module that will make use of the history of the correct or incorrect responses of the user to build a condensed representation of the knowledge state. Next, once we have a representation of the skill sets of the user, a reinforcement learning based agent will make use of that information to select an exercise from a fixed pool, which can provide the maximum expected knowledge gain for the user. Lastly, in the current implementation, we have a simple language model which takes as an input the selected exercise and generates a dialogue that can be played to the user. Now let's dig a little deeper into the knowledge module. Our current implementation consists of an encoder-decoder architecture. The encoder takes as an input the user history and encodes it into a single hidden state. The hidden state is a representation of the current knowledge of the user. In the decoder, this hidden state is used along with the test set of exercises to predict the performance of the user on them. Now, next, let's have a look at the reinforcement learning agent. We have implemented a simple reinforcement learning agent, which is trained using Q-learning. It takes as an input the knowledge state of the user, along with an embedding of a candidate exercise computed using SentenceBot, and computes the Q value of that exercise. The reward of the reinforcement learning agent at the end of an episode is based on the performance of the user on a fixed test set. In our training, we made use of simulated learners that are based on Bayesian knowledge tracing to emulate real user.
All right, so here are the results of our current approach. These metrics were calculated against the truth values of the knowledge state, which was generated by the Bayesian knowledge tracing module. We received a competitive score of 0.43 where F1 was concerned and AOC-RHC score of 0.77 in the knowledge tracing module. As mentioned before, the aspect of reinforcement learning for exercise selection is quite novel. Hence, we implemented a random policy as a baseline which saturated after 1500 episodes. Here, an episode denotes a set of exercises. However, our policy yielded better results, saturating at around 300 episodes with the knowledge state known and around 500 episodes when the knowledge state wasn't known. Now we'll see the analysis.
Our knowledge tracing model performs slightly below the baseline models. This may be due to the fact that we exclude features such as exercise formats and user ID, which do not occur in day-to-day conversations. But these are included in the baseline model, which are specific to Duolingo exercises. Secondly, in order to input the entire state into our reinforcement learning agent, we also compress the user's knowledge state into one single vector. This is not done in top performing baseline models. A possible explanation for the improved performance of our RL agent over random strategy is that the agent comprehends the relationship between the knowledge state and the SentenceBot embeddings generated for each conversation. This understanding enables the RL agent to optimize the selection of conversation, focusing only on those sentences that can best enhance the knowledge state.
Our results demonstrate proof of concept that reinforcement learning can be integrated with an online knowledge tracing model to better select exercises and improve user learning. This type of model can prove useful to any learning task in which the knowledge state of the user can be tracked beyond just second language acquisition. For our next step, we plan to deeply analyze the policy of our reinforcement learning agent to see if there is more we can learn about what the exercise scheduler has chosen. A notable improvement to our system for future work would be to create a generative model as an abstraction layer on top of the exercise scheduler. A generative model would allow for more personalized and unique user experience, which could help amplify the learning benefits of the model. Next slide, please. Thank you for your attention. We would be happy to answer any additional questions if you reach out on either Piazza or email.